Okay, what's the definition for an eigenvalue and eigenvector?
Eigenvalue,
First
like,
answer is false. You know why this one's false?
yeah, I mean,
The
that would
definition is a
be,
two-part definition, and x can't be zero.
oh, yeah. So that,
That's the piece that always throws students, they always latch onto this, but they forget that it can't be zero. So I would say an overwhelming majority of time, students will say true there when it's false. Because it's not just for some vector, gotta make sure it's not for the zero vector. It's a little tricky. If you're not for sure, you always want to definitely ask there if you have to. But sometimes you might see it like this. Now, it's always true if x equals 0, because if x equals 0, does that mean that 0 is always an eigenvector? And this would kind of indicate, too, if you had this situation, what values would make this thing work. Every single real value out there. And that will destroy all mathematics, because that would say that every polynomial has every root out there. So a quadratic will have like 10 roots and then 20 roots. And that's not possible. Okay, anyways, V. So V is an eigenvector corresponding to eigenvalue 2. So we already know that V can't be 0. And this is an eigenvector corresponding to the eigenvalue of -2. Okay, once again, use your definition. If you're not for sure, go back to it. And if you were to plug in -v, first off, you do know this. If you plugged in -v, you can pull the negative out, apply this, but you're going to have to take that negative and absorb it back in and capture it with the v, like that. So what does it say then? It's false.
oh,
So any scaling of an eigenvector is still an eigenvector. You scale it by 1, 2, -1, it doesn't matter. It's still going to be eigenvalue or eigenvector. Okay, so what do you say about C?
that would be,
Okay, why is it false?
well, isn't the, like, the inverse and B just,
Okay, so what am I calculating right now? And this had a special name for this type of determinant. Remember what this one was called?
hear what it's called, but
Okay, it's called your characteristic polynomial. And you find the characteristic polynomial to calculate eigenvalues. This is the characteristic polynomial for A, and the roots for it are eigenvalues. But what is this characteristic polynomial equal to? characteristic polynomial of this matrix. So the eigenvalues for this matrix are the same as eigenvalues for this matrix. This talks about what's called a similarity transformation. So if it's invertible, then the matrices could have different set of eigenvalues. Wow, Joey, this is all false so far. They're not letting up at all, are they? All right, the next one's true though. Finally, they got through a true one eventually. So when it goes true, 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 I'm an accident, they'll eventually get one. Okay, yeah, this is kind of a no-brainer real quick. If you were to take this and then operate, there it is.
I mean, it's kind of like what we did.
Yeah, it's definitely false because if it's an eigenvalue with matrix, this has to be singular whenever you take it off. Otherwise, you're going to have a only trivial solution, not just a non-trivial. Good. All right, let's keep moving on. Does that all make sense?
Yeah.
Did you have a question about any of those, or?
No, I think I'm good on that.
Okay.
If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.